Hey everyone, this is Jeff Dew. Sorry I couldn't be in class today. Work got in the way. I'm sure we all know who that is. I'm doing ventilation generated patterns today, and I guess we'll jump right into it. Ventilation. All right. So ventilation is going to be the circulation of air in a space by one of many means, but generally what we're interested in would be natural wind convection. PPV fans, which would be positive pressure ventilation fans, NPV fans, negative pressure ventilation fans, and you can also get hydraulic ventilation, normally only done by the fire department, but there's a possibility it could happen somewhere else. Uh, let's see. Ventilation can be driven by many different things. You have natural ventilation, fire driven, and firefighter performed. Natural ventilation, what I refer to, is it's going to be like wind coming up to a building, creating a pressure differential. A higher pressure on one side as the wind strikes the building, and a lower pressure on the other as it leaves. Or even though a door with a crack in it can allow wind to get in and greatly affect the fire. Is a fire driven. As fire burns, it creates a pathway for the ventilation. It's very, very common to see fire driven ventilation in a structure that's nearly fully involved as the fire grows from one room to many rooms and starts hitting exterior walls or ceilings. It'll actually open areas in the building and ventilate itself. Not generally seen, from my experience, in a small fire, say one room and contents. But as fires get much larger, you'll start to see them ventilate themselves. And third, we have firefighter performed. As a firefighter myself, I've done a lot of ventilation. Generally, what this is done for is to move the heat and the smoke to make conditions more tenable inside. The goal is, one, to make it safer for the firefighter themselves, to control the fire, and if anyone's alive in there, to keep them alive. Generally, it's done through a roof, if possible, but that doesn't limit to a roof. It can go through doors, windows. We've cut holes in walls. It's all about where the fire's at and how you can get the heat out. And you see the unsealed compartments, doors and windows, holes in roofs. Unsealed compartments is any room you're in is not truly sealed. Technology is getting better and better these days, but you're still not in a true pressure-sensitive container where heat and smoke won't escape. It's just the level at which it will escape. Here I've got two pictures. We've got vertical ventilation, generally done by a fire department. You can see, everyone's probably seen or heard or seen a picture of a firefighter on a roof cutting a hole in a roof. This is generally done right above the fire to get the smoke out. It tends to intensify the fire because it draws more air in, but the overall result is much more positive than the negatives you create. On the right, I put a picture of fire ventilated so you can get an idea of what that's like. Basically, as you can see, the fire's gotten so large that it's burnt through windows, walls, and the roof and ventilated itself. At this point, I mean, with that building, that fire is almost out of control to where you're going to lose the structure. And when it gets to that point, if it ventilates well enough, it becomes a major problem in controlling a fire. So ventilation is done to control the flow of gases. You have doors, windows, other openings, pretty much anything you think that a hot gas and smoke can go through is going to be what your ventilation. And what it does is it increases the flow, velocity of flow over the combustible materials. So what you get is you get a greater airflow. So it doesn't choke out the fire as much because it's not getting depleted oxygen levels. So it tends to build the fire up more than it does put it out with, like blowing a match or anything. And what it can do is it will generally in a fire, ventilation draws the smoke and the heat. You create a pressure differential as you make an opening. So if you have one room in your house on fire and you open the window on the other side, it'll actually draw the hot gases and the smoke towards it. So we have what we call a well-ventilated area, which is one of great airflow. And it causes a couple of interesting effects. It causes faster fire spread due to the increased oxygen load and also blowing the heat around. I mean, if you move the heat into another room, you create a greater possibility for ignition. You get a higher heat release rate because you have more airflow over the embers and into the fire itself. What that'll do, it'll increase the charring. So as you move those hot gases around, before if you have an unventilated room where gas can only sit in the room it's in, it's just going to char around its one exit. But if you start ventilating and start drawing those gases more and more, increase the heat release rate, which would increase the plume temperature, you give it a better chance that it can increase charring as it touches surfaces and doors anywhere that the heat will build momentarily before it can escape. It also increases spalling and deformation. Same thing, higher heat release rate, higher plume temperatures. You're putting more heat in the room. It's obviously going to increase spalling, deformation, and charring. So we have in a well-ventilated room, you'll see areas with great fire damage, like just total loss of destruction. And these damage indicate, as you can imagine, high heat release rate, ventilation, or long exposure. I mean, it doesn't have to be a high heat release rate, but if it's there for a long time, you'll get the same effect. The thing to remember here is it's not always the point of origin. Due to difference in fuel types, it can make it very misleading. If you have say a slow burning fuel at first and then a fast burning fuel afterwards, it could burn for a long time, and that slow burning fuel then hit something with a high heat release rate, which will cause it to give the effect, but not necessarily where the fire was generated. So we have embers. Generally come from your fire, and ventilation has a great effect on these, because anyone who's ever built a fire in their backyard, you get the embers and you blow on them, and it causes a higher heat release rate, and it causes the fire to build. So when the airflow comes from ventilation, it raises the temperature as the airflow increases. And the more airflow, the higher the heat you're going to put out from this. And embers themselves, not just the heat related, but sitting on concrete next to metals, they can spall concrete on their own, they can melt metals, and they can burn holes through floors. It can be a source of ventilation if they burn a hole through a floor, if they spall concrete enough, or melt through the metal. And a lot of times what this gets mistaken for is ignitable liquids. If you set a pile of coals on a plywood floor, eventually it's going to burn a hole in the floor, which will draw air. So it draws air through this hole, increasing the heat and causing it to burn a bigger hole into the floor. And now you have what looks like a pool of gas or whichever ignitable liquid was on the floor, but instead it was actually embers that landed there, and with the ventilation caused burning and burnt through the floor. Another thing you get from ventilation is charring. It's very interesting to see and very helpful in seeing the direction the fire went and how it occurred. So in say a single room, a single compartment with a closed door, not super sealed, just a regular closed door, say a hotel room or whatever, what have you. As the fire builds, you have your hot gas layer on the upper section of the room, and as it approaches the door, it starts to escape through the cracks on the top of the door, and you have smoke and gases start to flow out. Well, you have a buildup of heat against the top of that door, and as you can see in the picture, you get a little bit of, it starts to char the door, and up towards the top will be heavier charring, and it will get lighter as it goes down the door. And also, cool air will generally tend to enter underneath as it circulates through, which will increase the charring at the top of the door. In a fully involved room where your gas layer reaches from floor to ceiling, you get another effect that's similar but a little different. Since the gases extend all the way from top and bottom, you have a very high pressure generated in that room. It'll start to force the smoke out above and below the door. So what you get is you get heavy charring at the top and the bottom of the door, but you get charring down the entire door. It may not be heavy down the entire door, but the entire door will be charred. And then if debris is placed next to the door is another thing to look at. And this is mainly to look between, see the difference between a fully involved room and a room with something burning next to the door. They'll have similar results, but a major difference. So as that debris gets next to the door, like the first room, the hot gas escapes through the top of the door, and it starts charring the upper portion of the door. The cool air is drawn underneath the door. And as it's drawn across these embers or whatever it's laying against the door that's burning, and that causes them to get hotter and hotter and actually start to burn the door itself. So what you see is you end up seeing heavy charring at the top of the door and heavy charring at the bottom of the door. But the main difference, the main characteristics to see the difference is that you don't have charring along the entire door, just at the top and just at the bottom. Ventilation can also affect your magnitude and your location. It has a significant effect on the growth and the heat release rate. It also greatly affects the pattern and formation. Like I said before, if you open a window, it's going to draw the heat and it's going to draw the smoke to it, and it can draw the fire that direction. So when you add more air, you get, in a better ventilation, you get a higher oxygen rate for the fire, a better flow rate to push the gases away from it. You get rid of smothering from the smoke layer. And ventilation also affects other things, the shape of the fire, the way it's going to burn. Is it going to burn across the room or just half the room? Is it going to burn across the ceiling in the attic? Like I said, the location. If it starts on a chair and you ventilate behind it, you're going to draw the fire backwards. Where if you ventilate on the other side, you'll draw the fire to yourself. It affects the magnitude, so the greater airflow, the bigger the fire builds. And the rate of spread, obviously, as you increase the heat release rate, you increase the products of combustion, you put more heat into the room and places for it to spread, and you're going to spread that fire faster. It's very common to find heavy damage close to ventilation points just because you've increased the heat release rate and the plume temperature so much right there. Ventilation is a very interesting aspect that it's sometimes good and it's sometimes bad. If a building naturally ventilates itself, or if there's ventilation going that's uncontrolled, it's detrimental to a structure because you have no control over where this fire is going to go. But it's the aspect of a firefighter when you come in and you ventilate. You're actually going to control. You may make the fire slightly larger, but you draw the smoke and the gas out, which will keep it from spreading. Other things, ventilation, seen fairly often. I mean, there's almost no fire you'll ever see that doesn't have some type of ventilation. But these are the main overview of what you see and the ventilation effects that you get from the fire.